Okay, so now we're in section 1.2. We're continuing our discussion of how to solve, the technique we would use to solve a system of equations. And we are working with small systems of equations, 2 variables, 3 variables, maybe even 4 variables. But the concepts you're learning can be applied to larger systems of linear equations. And in section 1.2, they're going to formalize the technique you learned on Monday to solve the systems in section 1.1. These row operations, getting the augmented matrix in triangular form, forward phase, backward phase, it's formalized here in section 1.2. So we're using this special row reduction algorithm that relies on using pivots to produce zeros in certain columns to turn the system of equations into one that's more understandable. Essentially, that's what we're doing, right? So let me see here now. Just gotta, yeah, there we go. So if we go to the next page here, they define echelon form and reduced echelon form. So echelon form has the 3 properties that you see listed below. All non-zero rows are above any rows of all zeros. Each leading entry of a row is in a column to the right of the leading entry of the row above it. Third condition is all entries in a column below a leading entry are zeros. Okay, now those properties are much more easily understandable if you look at some examples. So we're gonna get to some examples here. Now, if you further reduce a matrix to reduced echelon form, then you have 2 additional properties. The properties 4 and 5. Property 4 is that the leading entry in each non-zero row is a 1, and property 5 is that each leading one is the only non-zero entry in its column. Okay, so we solved a system of 3 equations and 3 unknowns on Monday, and we actually got that augmented matrix in reduced echelon form. Okay, so all right, let's go ahead and here and look at a few examples to help reinforce these concepts. Okay, so in the, and I'm kind of going back and forth here. Yeah, so, and if you click on in your viewer, there's a button to, if you double click, I think you can enlarge the picture. But you see how they have their, below the green box with the 5 properties, if you go down a little bit, it talks about triangular matrices of section 1.1. Okay, you see you have a triangular matrix on the left and then a triangular matrix on the right. Well, the first matrix where you have, well, I want to say this the right way. The first matrix is in echelon form. It's in echelon form. The second matrix is in reduced echelon form. So the first matrix in echelon form has a triangle of zeros below the diagonal. The second matrix in reduced echelon form has a triangle of zeros above and below the diagonal. You see the 1, 1, 1 there in the second matrix, 1, 1, 1. We call that, the coefficient part of the matrix. Above and below the 1, 1, 1 on that diagonal are zeros. And along the diagonal you have 1s. So that's in reduced echelon form. And in fact, that's the system of equations. We did an example where the system of equations reduced to that reduced echelon form on Monday. How many recall that? The second matrix there, doing that on Monday in the example. Okay, Cameron remembers that. And of course for the homework, you had that as well. So basically, reduced echelon form of a matrix is unique. If you get the matrix in reduced echelon form, that's that you can't break it down anymore. And so when we solve systems of equations, we want to, well, we get it in echelon form to determine if there's a solution, to help us determine if a solution is possible. Like for instance, in the first matrix there, if that were an augmented matrix, you see the bottom row is 0x1 plus 0x2 plus 0x3 equals 5 halves. That there's no solution x1, x2, x3 that'll work there. So you see the first augmented, if that's an augmented matrix, say the first matrix, that we wouldn't do any more row reduction on that. It wouldn't be practical because the system has no solution. Okay, but the second augmented matrix, obviously that has a solution. So, these properties really, just doing a lot of practice will help you understand the properties. It'll reinforce those properties. They talk about here in example 1, okay, in example 1 here, the following matrices are in echelon form because the leading entries, okay, may have any non-zero values. So the boxes may have any non-zero value. Now, what happens in the homework is they'll call those boxes for some reason. They'll call them X's, but just remember the boxes can have any non-zero value, okay, and the starred entries may have any value, including 0. Well, you see in example 1, those two matrices, you have a triangle. The way I think of this is you have a triangle of zeros below below the leading entries of each column. So like the first matrix there, the first matrix is a 4 by 4 matrix. And you have leading entries, the first black box and the second black box, okay? And below the leading entries, you have all zeros. You see that? You have all zeros. And the same for the second matrix. Okay, you have all zeros below the leading entries. So, but they're not saying that the boxes, the leading entries, the boxes don't have to equal 1. But if you look, and so the two matrices there, the top two matrices of example 1 are in echelon form. But if you go below here, if you go below the two matrices below, they're in reduced echelon form because the leading entries are 1s, okay? And there are zeros below and above each leading entry of 1. Do you see the difference between echelon form and reduced echelon form? In example 1 there. Okay, Mikhail's seeing that. It really helps to look at examples. And then that reinforces the properties. Okay, all right. Are there any questions on this so far? Okay, okay. Well, if you're good, then let us proceed on here. So hold on here. I got to go down a little bit. Yeah, any matrix is row equivalent to one and only one reduced echelon matrix. So when they talk about, any matrix, they're not saying the matrix has to be the matrix of like an augmented matrix for a system of equations. It could just be a matrix of values. But if no matter what row operations you do on a matrix, if you get it in reduced echelon form, it'll be the same. Like if you use row operations to get a matrix in reduced echelon form, and your friend does different row operations and gets the matrix in reduced echelon form, the reduced echelon form of the matrix for both you and your friend should agree. Reduced echelon matrices are unique. Matrices in echelon form are not unique. Okay, all right, so far are we okay? All right, we're good. Let me just see here. All right, very good. I'm just taking our time here. So in terms of notation, they say at the top here, if a matrix is row equivalent to an echelon matrix U, we call the matrix U an echelon form of A. So when they say a matrix is row equivalent to another matrix, that means that if you do elementary row operations on the matrix A, and you arrive at this matrix U is row equivalent to matrix A. And the elementary row operations are the ones that we learned about on Monday in section 1.1. You can have replacement of one row by the sum of itself and a multiple of another row. You can interchange rows, or you could scale rows. Scaling means multiplying all entries in a row by a non-zero constant. Okay, so the elementary row operations are designed to preserve like a system of equations. If you're reducing the system of equations to a system of equations that's easier to understand, you have to do row operations that don't change the equations. And that's what elementary row operations are in section 1.1. Okay, so we talked also a little bit about pivot positions. Okay, so pivot positions, I think I can highlight here. Yeah. A pivot position, I want to be just careful here. I don't want to get too hung up on terminology here. Let's just go to example 2. We talked a little bit about what a pivot is, what pivots are. But here in example 2, you have a matrix A. It's 4 rows by 5 columns, and they want you to row reduce the matrix A to echelon form and locate the pivot columns of A. Well, pivots are used in a column. A pivot is used to produce zeros in the column below the pivot. So what they do in matrix A, well, if we look here, and maybe I can highlight here to help a little bit. Here's the matrix A, and then hold on here. Here's they do a row operation. What row operation did they do? Going from the matrix A to the next matrix. They did a switcheroo. That's right, Mikhail. They switched. Well, you can see the second and third rows remain the same, but they interchanged rows 1 and 4. Okay, so that was the row operation. Now what they're going to do, you see, is they're going to use the 1 as a pivot to help produce zeros where the -1 and the -2 are below the 1. Okay, so if we go here, let's go down a little bit. And let me see, maybe let's look here, okay, at this matrix here. So you'll notice the second row in the highlighted yellow matrix has numbers 0, 2, 4, -6, -6. How did they get that? Well, in the matrix above, they used the 1 as a pivot. So if you were to just add the first row to the second row, okay, and replace the second row with the sum of the first and the second row, then the second row would be 0, 2, 4, -6, and -6. And if you look at the third row now, it has 0, 5, 10, -15, -15. So what row operation was done on the matrix above to get that third row? What did they have to do with the first row?
2.
That's right. Multiply. That's right. I see. Multiply the first row by 2, and add it. And you can mentally, if you multiply the first row by 2 in your mind, you're going to have a row that has 2, 8, 10, -18, and -14. Right? That if you multiply that first row by 2, in your mind you have a row that has numbers 2, 8, 10, -18, and -14. Well, if you add that row to the third row, okay, the third row, it has -2, -3, 0, 3, and -1. If you add that and then replace the third row with the sum of those rows, you'll get what you see there in the highlighted matrix there. A third row would be 0, 5, 10, -15, -15. So you see, you use the one pivot, the number 1 pivot, to produce zeros in the first column below the pivot. That's the goal, right? We want to get zeros in the matrix, okay, using the row operations. Now what we do is we move over to the second column, and we'll use the 2 as a pivot for the second column. Okay, so you see there you have a 5. If we look at the third row with the 0, 5, 10, -15, -15, where the 5 is, we want it to be a 0. So what number times 2 equals 5? What number times 2 equals 5? What fraction times 2 would equal 5? 5 halves. That's right, Belen. And so what we'll do is we'll multiply. We want to multiply the 2 by -5 halves and add it then to the, and that'll give us -5. That's right. So you see, but you have to multiply the whole second row by -5 halves and add that to the third row. So you see, and then also to remove the -3, to make the -3 a 0 in the second column, you're going to have to multiply the second row by 3 halves, and then add that the transformed second row to the third row. All right, and so I mean basically, let me see here, and they do that on the next page. Let me go down here. So now they do both those row operations, and they arrive. Whoops, hold on. They do both those row operations, and they arrive at that matrix. Well, of course, Mikhail, we love it when we get a bunch of zeros in a row. That's great. So now what we want to do is to get it in echelon form, we have to, we're going to take the fourth row. I suppose so, Mikhail. I'm not familiar with Tetris, but I'll take your word for it. If we interchange the third and fourth rows, okay, if we do that, okay, that will get us here. And, whoops, hold on. Did I lose the book here? One moment. Give me one moment here. This happens occasionally. One moment. Let me just get it. Let me get it back here. One moment. This happens occasionally. One moment. Okay, so now we have in the, and I want to make sure not too much is highlighted here. Now in the highlighted matrix, that is in echelon form. And you see there are three pivot columns. The first, second, and fourth columns are pivot columns. Okay, those are your pivot columns. Are there any questions on this? I'm trying to just do this example with you and talk about it because the terminology is going to come up in your homework. Those multiple choice problems, for instance, they'll talk about pivots and pivot columns and so forth, and you have to know conceptually what those mean. A pivot, hold on here. I'm trying to highlight this, but it's not being cooperative. Here we go. Yeah. So a pivot basically, did I lose the book here, class? Did the book go off again? It's black now. All right, hold on. One moment. I have another way. I have another book. Don't worry. If I need to do this.
Well, it got back right after it went black.
All right. Thank you. Thank you. Let me know if it goes black, class. And I'll okay, so a pivot is basically a non-zero number that is used as needed to create zeros via row operations. That's what a pivot is. So they talk about, of course, they give steps. They in example in section 1.2, they talk about the row reduction algorithm here, and they talk about the different steps involved. But if you just do enough practice, you're going to be fine. I don't want us to I want us to learn by doing, and not thinking about steps, this step, that step, what steps next. You know, we're just gonna do it and learn that way. I will mention that you know, we like to use generally small numbers or ones as pivots. One is a very good number to use as a pivot in a column because it's easy to do row operations when the pivot is a one, so that you can produce zeros below the pivot in the column. I will mention, this is worth mentioning here. So they do another example, but we already went through an example. So let's just, I want to get to this numerical note here. So this numerical note, I'll highlight it here. don't worry about step 2 above, but when a computer, like a computer program like MATLAB, okay, when it does the row reduction algorithm numerically, it will actually use the largest number in a column as a pivot, not the smallest number. And that's called partial pivoting. And the reason the MATLAB will do that is because it reduces round off errors in the calculations. That's what's going on there. So you're actually going to have a MATLAB assignment in a while. It'll be a while because you have to learn some linear algebra here, but you're going to have one that deals with the partial pivoting because I think it's good to know. So let's go ahead here, and I want to get right to an example. Here. So I want to, yeah. Let's go ahead and copy this example down. Let me give you a moment to copy it down. All right, very good. Okay, so here, well, I know you need a little time to copy this down, but let me see here. Let me use my stylus. Okay, they want us to find the general solution of the linear system whose augmented matrix has been reduced to this augmented matrix. So we understand that on the right side we have the constants. So like the the first equation here, the first row, Well, how many variables are there in this problem? How many variables? Good, 5. So the first row reads 1. Good, Cameron. Good, Belden. 1x1 plus 6x2 plus 2x3 minus 5x4 minus 2x5 equals -4. So what they're saying is here they're giving you a reduced augmented matrix. And by the way, what form is this matrix in? Is it in echelon form or reduced echelon form? Cameron and Yasin say echelon form. That's absolutely right. That's absolutely right. Now, to get it in reduced echelon form, you would need to, for instance, the 2 here would have to be equal to what? What would that leading entry have to equal for reduced echelon form? Good, Mikhail. It would have to be 1. Okay. And also for reduced echelon form, what would, I want to be careful how I say it. That's right. We would need to have zeros there and there. And is there any other place where we would need a 0 to get it in reduced echelon form? Any other spot? Above the 2. Above the 2. Because because the 2 and the 1, well, and this one here, those are leading entries. Those are leading entries. Okay. Okay. So if you look along the row, it's the first, if like the first row, the 1 is the first non-zero number. The second row, the 2, is the first non-zero number. It's a leading entry, you see? And okay, so let me ask you this. Is this a consistent system? Is this a consistent system? It is. It is. Because we don't see any problem here. The last row here reads 1x5 equals 7. So we're not going to have an issue with that. Now I got to be a little bit careful here. You know, you could have a, well, I want to be a little bit careful. Well, no, that's fine. That's fine. Let's just keep it kind of simple. But let me just see one thing here. I want to just write something down real quick. Yeah, let's do something very simple here. Suppose, I want to be a little bit careful here. I know what I want to say. Whoops, hold on. I don't want to do that. Hold on. Let me get that back. I know what I want to say. You know, if you had an augmented matrix like this, let's say you had 0, 1, and 7. And let's say you had 0, 0, 1. What students tend to do is they tend to look at the bottom row. And again, if this is an augmented matrix, the bottom row would read, right, it would read 1x2 equals 7. And they'd say, oh, it's consistent. But as Mikhail noted, the first row here, the first row reads 0x1 plus 0x2 equals 1, and that's inconsistent. So sometimes what will happen is the bottom row will give you an equation that's okay, but you'll have something in the middle that isn't quite right, and that's right, Yasin. So you got to be careful. You know, you got to be careful, especially how many find those multiple choice questions that they're very conceptual, but how many find them? Oh, they're got to be careful on those. They're a little tricky sometimes. How many are noticing that? The multiple choice questions. Yeah, and you know they're a little tricky because they're trying to test your understanding, you know, of the and David and Yasin know what I'm talking about. But all right, well, we want to find the general solution. So what we're going to do is we're going to try to get this augmented matrix here in reduced echelon form. Okay, and so let's go to the next page here. And we're going to use, naturally, we're going to use row reduction to do this. So what I have here, what I have is a solution. So this just means solution. And we know that the matrix is in echelon form, but we want to get it in reduced echelon form before solving for our basic variables. Okay, and don't worry about this here. I'll just wipe that out. Now, what are basic variables? Well, you're going to see. You're going to see what basic variables are. Let me give you a moment to copy this. So when we do the backward phase, so for this problem, the forward phase has already been done to reduce the augmented matrix into echelon form. That's this form. But now what we want to do is we want to produce zeros in these spots. This is the backward phase. So what we're going to do is we're going to work from the right to the left. So we'll use the 1 in the bottom there as a pivot to produce zeros where the -2 and the -1 are. So what do? Well, we're going to multiply the first row by 3 and add that to the second row, and then replace the second row with that result. And it's all so I can get a 0 where that -1 is. To get a 0 where the -2 is, I'm going to multiply the third row by 2 and add it to row 1, and then replace row 1 with that resulting row. Please let me know if you have any questions. Please let me know if you have any questions at all.
Is it required to change all the leading numbers to ones before converting numbers above them to zeros?
You don't, it isn't required, but generally what I like to do is I like to do that, because if the leading entries are 1s, then it makes the row operation just a little clearer. I mean, you don't have to though. What I did, getting down to now this matrix here, is where the 2 is here, I wanted that leading entry to be a 1. So I took the second row and scaled it by half, multiplied by half, and then replaced the second row with 1/2 that row 2. And so you see, I'm trying to get this in reduced echelon form. So in reduced echelon form, all the leading entries are going to be 1s. So I might as well make it a 1 now. You see, that's what I decided to do. But you can make it a 1 later. That's okay.
Oh yeah, so like in this case, the 2 paths you can take are either convert it to a 1 by dividing by 2, and then just modify the top row by 2 times row 2, or just multiply by the row and then divide the second row by 2. It'll be the same result, right?
Say that again, Mikhail, please.
Okay, so there are 2 paths you can take to the final matrix. So you can either scale the middle one by 1/2, and then just replace the top one with the sum of it plus 2 times the row 2, or you can just
or -2 times row 2, right?
Yeah, negative. Or you can do
which by the way is what I did here. Okay, continue.
And
Yep.
the other way you can do it, which is for some reason what my first intuition was, just replace the first row with -1 times row 2, and then scale row 2 by 1/2.
Yeah, you could do that. You could take the second row and multiply it by -1 and add it to the first row, and then do the scaling later. Yes, absolutely.
Okay, yeah.
And your reduced
Same
echelon
result.
form matrix will be the same as mine. It'll be, that's right.
Okay. Okay, thank you.
All right, you're welcome. You're welcome. So now this matrix here, and I like to kind of delineate things. Notice, by the way, I have the tildes. So like, the matrices are row equivalent. So this system of equations here is equivalent to my beginning system of equations. And this is now in reduced echelon form. This is reduced echelon form. So looking at this, looking at this augmented matrix here, how many equations are there? How many equations do you see? It's a consistent system. That's right, Cameron. There are 3 equations. That's right, Belen. And how many variables are there? 5 variables. So this is an example where you're going to get an infinite number of solutions. So to see this, what we'll do is we will take this augmented matrix here and rewrite it back into an associated system of equations. That's right. We're going to have 2 free variables. That's right, Mikhail. We're going to have what we call 3 basic variables and 2 free variables. So if we go to the next page, and I'm sorry, was everybody good? Everybody good on this so far? Are we ready to go to the next page? All right, I'll take that as a yes. We go to the next page, and here is now our system. The matrix is in reduced echelon form, and this is the associated system of equations. So what we want to do, right, is we want to get the solution x1, x2, x3, x4, x5. See, now in linear algebra, you go beyond 3 variables. We want to know what the set of solutions are. Okay, those 5-dimensional coordinates. Okay, what would that solution, what would that space look like? Well, x5 is 7. Okay, so that's easy enough. Maybe I can do a little, so x5 equals 7. That's a basic variable. And when we look at the second equation here, you have 1 equation and 2 variables. That means one of the variables has to be a free variable. So we'll let x4 be free. We'll let x4 be free. And in that case, x3 is equal to 5 plus 4x4. Okay. X3 is a basic variable. Basic variables are variables that either have values or they can be written in terms of free variables. Finally, we move to the top equation. Okay, the top equation, all right, x1 is equal, well, we already established x4 is free, but now we have to let x2 be free. And so x2 is free, and x1 is negative 6x2 minus 3x4. See that, how it works? So you have two free variables and three basic variables. And this means then, since x4 and x2 are free, there are infinite number of solutions. And it makes sense because you have hold on here. You have three equations with 5 unknowns. It's an underspecified system, so to speak. Okay, and I'm going to ask you something here then. Let me ask you this. Would the point 0, 0, 5, 0, 7, would that be in my solution set? My solution? Mikhail says yes. And if and the answer is yes. Because in terms of x2 and x4, my free variables, for this particular point here in 5-dimensional space, x2 would be what and x4 would be what? What would x2 and x4 equal? That's right. That's right, Cameron. They'd both be 0. So you see, free variables, you can let them be any value. And then you determine the value of the basic variables. Let's say that x2 were equal to 1 and x4 were equal to negative 3. Okay, well, what would the coordinate be? If x2 equals 1 and x4 equals negative 3, let's see. So what I'm trying to do is I'm trying to, I have 1, 2, 3, I have 5 coordinates. 5 coordinates here. So let me see, what would x1 be? Well, x1, you're faster than I am. Hold on. Mikhail and Belen are saying that the coordinate would be what? 3, 1, -7, -3, and 7. Okay, let's check that out. Let's check that out. So let's see, x1 would be -6 times 1 minus 3 times -3. Yeah, that does equal 3. I agree. So the 3 is right. So 3 is good. 1 is good. X3 is 5 plus 4 times x4. That is -7. Yep, that's right. Good. So you see, we could do this all day. We could pick different values for x2 and x4 because they're free variables, and then we can solve for the basic variables. And what happens is you generate some subspace in five-dimensional space because the points have 5 coordinates. You see that? These set of equations here, describe a space or a subspace of a 5-dimensional space. You see? So you see, now we're moving on from finding like solutions that are just one point to solutions that are where you can have an infinite number of points. And incidentally, the well, yeah, that's fine. Are there? This relates actually to example 4 in the textbook. Example 4. Okay, I'm just seeing here. I'll mention one more thing here. Well, are there any questions regarding this example? Maybe give me a thumbs up if you're feeling good with it, if you're feeling okay. Okay, Mikhail's good, Belen's good, Jonathan's good, Marcella's good, wonderful. All right, are there any questions at all? Yasin's good, wonderful. Okay, I want to mention here you could think of these free variables as also like parameters, right? You could think of those as parameters too. But let's see, Cameron says, how would you depict this with 5-dimensional space? Well, you can't visualize the 5-dimensional space, but mathematically it exists. It exists. We live in 3-dimensional space, and we interpret things. Yeah. Well, I got to be a little careful, right? If you worry about like special relativity, then you have time as a 4th dimension. But we won't worry about that here. Let's not worry about that. Let's, when we look around the world, we're looking in 3-dimensional space. but you know, that doesn't mean you can't have a 5-dimensional space, you see? And I mean, it's really fascinating. And these are the kind of things that in linear algebra you can touch upon that, you know, that you might not see so much in other courses. Now, I'll mention another thing here, a numerical note given at the end of the, towards the end of the section 1.2. So remember, if you had, you know, if you had 100 equations with, you know, 100 variables, or 100 equations with 150 variables, you know, you'd be using a computer to reduce that, the augmented matrix to reduced echelon form. But every operation you do requires a flop, right? Well, in general, the forward phase of row reduction takes much longer than the backward phase. And you might have noticed this even in your homework, that once you get, how many notice once the forward phase is done, once you get the augmented matrix in echelon form, then it's kind of, the problem sort of, I mean, that's, I want to say it the right way. That's the quote hard part's done. How many kind of feel that way? Or the hardest part is done. Yeah, that's what they're getting across. Mikhail and Jonathan, yes, that's right. And an algorithm for solving a system is usually measured in flops. A flop is one arithmetic operation, plus, minus, multiply, or divide. How many have heard of a flop, like in computer science, a flop? That's a computer science term, right? Well, yeah, well, okay, in basketball, sure. XD, I'm not sure, Cameron, what XD is, but what was that? Well, we call it an arithmetic operation, a flop. And you know, what can computers do? Computers, when you get down to it, they multiply, divide, add, and subtract, right? Those are the operations that go on in a computer. And so we use those to do our row reduction. So it's very important doing row reduction as efficiently as possible, because that'll cut down on computing time if you have a huge system of equations. They talk about, if you have an n by n plus 1 matrix, the reduction to echelon form can take 2n cubed over 3 plus n squared over 2 minus 7n over 6 flops, okay? Which is approximately 2n cubed over 3 flops when n is large. In contrast, further reduction to reduced echelon form needs at most n squared flops. So what they're saying is the forward phase, where you get the matrix in echelon form, that takes more flops than the backward phase to get the matrix in reduced echelon form, because 2n cubed over 3 likely will be more than n squared. How many think that's these numerical notes are kind of fascinating? How many think that's kind of good stuff? That Cameron, you're right. You're right. Time complexity for programming. That's right. I mean, the more flops it takes, the longer the computing is going to take. And even with computing power these days being pretty good, we still have to worry about it. But computing power is a lot better than like when I was your age. When I was your age, you know, well, younger, but you know, back then, you know, Pac-Man was like, oh wow, you know, Pac-Man. There's a Pac-Man game. You know, how many have seen Pac-Man before? The computer. Yeah, it's a kind of an old-fashioned game and video game. But now you got, you know, three-dimensional games. I don't know if you've heard of this game called Resident Evil. I see it sometimes on the internet, like in YouTube, like there'll be, I probably don't know if I should say that during lecture, but it's a game that is like three-dimensional, and I mean, there are other games, right? Like, what are some other three-dimensional video games that are like really popular now? Fortnite. Okay, I've heard of that, Jonathan. You know, well, and you know, behind all that computer, behind all that, what's the word I'm looking for? There's a word I'm looking for. Behind all of those computer graphics, Doom, Eterna, there's computations going on, right? And you're going to actually see that in chapter 2. But on that note, let me stop there. I want to give you some time to work on the new section 1.2 free response exercises. So if there are no more questions, I will stop the recording and give you some work time here. Are there any questions? Okay, I'll stop the recording.